Okay. Now here. Okay. Perfect. So we'll see in the next chapter the activity of this compound able to isolate the neuronal firing, and so they can stabilize the activity of the different neurons inside the CNS. Two important classes of compounds act as a sedative or hypnotic. These two classes are barbiturates, a very, very old class of drugs, and benzodiazepines, more recent. And so we'll see the chemical structure, the way of action, the mode of action of these two different classes. These two classes interfere with an important activity of an important neurotransmitter called GABA, gamma-aminobutyric acid. This neurotransmitter is an inhibitory type transmitter. It has a very, very simple chemical structure. You see here on your left the chemical structure of the gamma-aminobutyric acid. You see 1, 2, 3, 4 carbon atoms. In alpha position, you have the acidic function, the carboxylic group, and in gamma position, 1, 2, 3, 4, on the fourth carbon atom, you have an amino, a basic function. This neurotransmitter is an inhibitory type neurotransmitter, and its activity is counteracted by another important neurotransmitter called glutamic acid. You see on your right the chemical structure of the glutamic acid. Once again, you see the difference between these two important neurotransmitters is due only by a carboxylic function. In the case of glutamic acid, you know, glutamic acid is an acidic amino acid. It has two carboxylic functions, while gamma-aminobutyric acid has the same chemical structure, but only with only one carboxylic function. So these two neurotransmitters are very similar, but they have the opposite, completely different activity on CNS. Barbiturates and benzodiazepines are able to amplify the activity of the gamma-aminobutyric acid. So they're able to increase the activity of this important neurotransmitter by different mechanisms we'll see in the next slides. Here you can see the biosynthesis of GABA. It can derive directly from glutamic acids by the activity of a particular enzyme called GABA decarboxylase. You see, GAD, G-A-D. So it is sufficient a decarboxylation, a simple decarboxylation of one of the two carboxylic functions of the glutamic acid to have GABA. And then you can see other pathways starting from ornithine. Ornithine is another important amino acid. You see ornithine can be deaminated and oxidized on the 1, 2, 3 on the fourth carbon atom, oxidized to aldehyde, further oxidation to carboxylic acids, and then decarboxylation, to give glutamic acid, and then decarboxylation to give gamma-aminobutyric acid. Another pathway starts from putrescine. Putrescine is a compound which belongs to an important family of compounds called polyamines. Putrescine, you can imagine the smell of this compound. But this class of compounds called the polyamines are very important for the cell growth, for the cell development, and in particular spermine and spermidine are very common in cosmetic compounds because they are used for the cell growth of skin cells, hair cells, and so on. However, putrescine represents the starting point of these important pathways. Deamination and oxidation to aldehyde, you see, to give 4-aminobutanol, an aldehyde, and then further oxidation of the aldehyde to carboxylic acid to give gamma-aminobutyric acid. Here in the other picture, you can see the metabolism of gamma-aminobutyric acid. Once again, deamination and oxidation to succinyl aldehydic acid. You see, it's a particular acid with an acidic function and an aldehydic function. And then reduction to alcohol, here to give gamma hydroxybutyric acid, yes, or further oxidation to succinic acid. So here in the picture you have the biosynthesis and the metabolism of this important neurotransmitter. GABA is not able to pass the BBB, blood-brain barrier. So, if it is necessary, its administration, we have to inject directly in the brain. It's impossible. However, once again, you can see that charged compounds are not able to pass the BBB, blood-brain barrier. Inside the synapses, there is an important reuptake system of this neurotransmitter, because you know the different mechanism inside the synapses to recover part of the neurotransmitter in order to use again this neurotransmitter. GABA is located particularly in substantia nigra and hypothalamus. But which are the receptors able to interact with the GABA? If you know to have a classification of different receptors, it is necessary to have selective compound able to interact only with a specific class and not with other classes. So in this case, you can see where GABA receptors interact, GABA interact. You see the classification of GABA receptors. We have two main families of GABA receptors. The first family is inotropic receptors. The second family, metabotropic. Inotropic family, GABA A and GABA C. Metabotropic, G protein, GABA B. We are interested only on GABA A, the first class. We are not interested on GABA C and not on GABA B. Only GABA A are involved in the sedative activity. Here in the picture you can see two different ligands able to interact only with a specific family. In particular, you see bicuculin blocks GABA A receptors, or baclofen is able to activate only GABA B. If you see very carefully the chemical structure of baclofen, you can recognize the skeleton, the backbone of the gamma aminobutyric acid you see here. 1, 2, 3 amino, 1, 2, 3, 4. And you can see an additional aromatic rings in position 3. Yes? Allora, sì.
Scusa una cosa, hai il numero dell'Angelini per caso?
Dell'Angelini?
Perché aspettano dalle 9, ma secondo noi ci si è scordata di fare lezione, ma non abbiamo il numero per chiamare. Sabrina mi sa che si chiama.
Aspetta che ci guardo un secondo. Scusa. Just a moment, dear students. Aspetta un secondo. Penso di no, sai.
Il lavoro non ce l'ha, è solo la mia.
Aspetta un attimo. Come si chiama?
Sabrina.
No, non ce l'ho.
Non ce l'hai.
Aspetta, però potresti chiamare la Patrizia Relia, che è quella che lavora con lei.
La sorella della Silvana?
Sì.
Ok, mi dai il numero della Patrizia quindi?
Sì, te lo giro.
Ah, bravo.
Te lo giro su WhatsApp.
Bravissimo. Dico la di chiamare la Patrizia e di farsi dare il numero dell'Angelini.
Io penso che sia l'unica maniera per farlo,
perfetto,
perché
faccio così.
Non ne ho altri.
Grazie,
Non figurati.
Scusa, mi disturbo.
No, niente paura. Adesso riesco a condividere il contatto. Okay. Sorry, dear student. Okay. So you see here once again. Okay. Here in the picture you can see two important ligands for two different types of GABA receptors. And I remember you again the difference between an ionotropic receptors is a channel receptors with a metabotropic receptors, which is a protein G receptors, G protein receptor. Here you can see the location, the difference of location of GABA A and GABA B. GABA A widespread postsynaptic, GABA B pre and postsynaptic, you see. In particular, here you can see the function, the main function of GABA A, an increase of chloride ions with a minus charge inside the neurons. So you can understand that if we increase the influx of minus charge inside the neurons, we can stabilize the membrane potential. We can stabilize the activity of the neurons. And we can block the transmission of action potential. Because we stabilize, we decrease the membrane of the neurons. We decrease the potential. You see, we can have negative values of the membrane potential. So, benzodiazepines are able to prolong the activity of GABA on a GABA A receptor. Perhaps we can open for more time this type of channels, and we can increase the quantity of minus charge inside the neurons. GABA B are completely different receptors, metabotropic receptors, and they modulate the entrance of calcium ions. But this is a completely different mechanism, a completely different receptor. So we are interested on only GABA A receptors. In particular, we'll see that barbiturates and benzodiazepines are able to modulate the activity of only GABA A receptors. Here you can see a long list of different compounds with different activities on the two ionotropic GABA receptors, GABA A and GABA C. For example, you see bicuculin is an antagonist of GABA A and no active on GABA C. Baclofen no active, picotroxycinin antagonist, and so on. But please note the activity of the benzodiazepines. They are defined as allosteric modulator. This means that the interaction of benzodiazepines with this type of receptors, GABA A, this interaction is able to change allosterically the conformation of the receptors in order to increase the activity of gamma-aminobutyric acid, of the neurotransmitter. You see also other compounds, triazole, pyridazine, imidazopyridine, but barbiturates. Also, these compounds can be considered allosteric modulators. And these compounds are not active on GABA-C, the other class of ionotropic receptors of this family. So we'll see that benzodiazepines are not agonists because they act not on the active side of the gamma-aminobutyric acid, but they are considered allosteric modulator because they can modify the conformation of the active site in order to prolong the activity of the natural neurotransmitter gamma-aminobutyric acid. Is it clear, this concept? Okay. Once again, you can see the activity of the GABA receptors. They mediate a fast synaptic transmission by movement influx of chloride ions. So, activation of postsynaptic GABA-A causes a hyperpolarization, an increase of the negative values of the potential, the membrane potential of neurons, with the consequent decrease of the neuron to transmitted excitator impulse. We can block the transmission of the action potential. You see here the location where this type of receptors are located inside the CNS, in particular regions you see of the brain. How this type of receptors are organized? Here you can see a picture of this type of receptor channel receptors. And you see different sites of interaction of the different classes of compounds, able to modulate, to modify allosterically the conformation of this receptor. So the site of benzodiazepines is different from that of barbiturates, of neurosteroids, and picrotoxinin and other compounds. Here you can see a cross-section of the receptor. You can see that it is organized in 5 subunits. In the middle you can see the channel reserved to the chloride ions. And here in red you see a picture of the GABA-C receptors. Also, this type of receptors are channel receptors, but benzodiazepines, barbiturates are not able to interact to modulate this type of receptor. GABA-C not respond to the same ligands. Which are the ligands able to modulate the activity of GABA-A? First of all, in the picture you see that the benzodiazepine binding site is different from the binding site of GABA. So we cannot define benzodiazepine as agonists because they don't act on the same active site of the neurotransmitter. They act in a different site located among 10 angstrom from the GABA, from the active GABA site. But the interaction of benzodiazepine with their site is able to modify allosterically the whole structure of the receptors in order to prolong the interaction with the GABA. But there are also other ligands with the same activity of benzodiazepines. In particular, you can see barbiturates, the next class of drugs that we'll see, steroids, ethanol. Ethanol is able to modulate the activity, to prolong the activity of GABA on this type of receptor. This means that if you assume benzodiazepine together ethanol, you have a very potent synergistic activity. You can sleep for 3 days. My father, more than 20 years ago, took a tablet of Tavor with the snaps, with the grappa. So I don't know the name in English, but it's a strong liquor with a lot of ethanol. And I remember well, he slept for 3 days, and it was impossible to awaken him, really. And so please remember this synergistic activity between benzodiazepines and ethanol. But also gaseous anesthetics. We'll see this class. It's a future chapter of the course. Diuretics, metal ions, divalent cations, and so on. So it is possible to potentiate, to increase the activity of GABA by using drugs, but also other type of substances. You can appreciate the structural diversity of compounds able to interact with this class of receptors. This means that there are a lot of active sites which after their activation are able to modify, to allosterically modify the conformation of the receptor. Benzodiazepines are quite recent drugs for CNS discovered in 1975. Before benzodiazepines, there was another class of drugs used to increase sleep, to modulate the activity of GABA, and this class was represented by barbiturates. Barbiturates are very old drugs discovered at the end of the 18th century. But barbiturates have a problem. A small quantity, a small dose of barbiturates can block the center of respiration. So the barbiturates are very dangerous drugs. It is not the case of benzodiazepines. Benzodiazepines are not so toxic. You can take 20 tablets of Tavor without any problems. Okay, perhaps you can sleep for 2 or 3 days, but without any other problem. And they were discovered recently, and you see which the interaction of benzodiazepine with GABA-A. You can see the classification, how we can describe this type of receptors. You see GABA-A 1C2 means GABA-A 1 alpha, gamma 1 beta 2 units inside the receptors. Okay, this is just a description of this type of receptor. But as I told you before, benzodiazepines have not a direct action on the receptor. In the past, at the beginning of their discovery, they were defined as agonists. You see, full agonists. Because some compounds of this class are able also to act as inverse full agonists. This means that they can have the opposite activity. We are not interested in this type of compounds which have an excitatory activity. There is another group of benzodiazepines called in the past as antagonists. This means that these compounds are able to interact with the active site. They are not able to activate the receptor, but they occupy the receptors. So they represent a class of compounds which can use for high dosage of full agonists. We can block the receptors against the activity of the full agonists. We'll see their therapeutic use. However, you can see the biological responses of different benzodiazepines. The agonist, the older definition, they can be sedative, anxiolytic, anticonvulsant, enhancing effects of alcohol, but also they have an amnesic activity. Amnesic. In particular, on the short memory. This means that if you take a pill of Tavor the day before of your exam, perhaps because you want to sleep, the day of the exam, it's difficult for you to remember a lot of things. So I suggest you to not use this type of compounds the day before of exam. Perhaps if you want to forget a love story with some guys, it's useful to use this type of compounds, but not in the case of exam. This is my personal suggestion. And the effect is directly on the short memory, not on the long memory. And it's interesting. Other benzodiazepines can be considered antagonists. So you see no any activity on the receptor. And then there is other benzodiazepines that can be considered inverse agonists, paradoxic effect. Stimulant, you see, increased cognition, anxiogenic, convulsant, antagonize effects of alcohol. But in the therapy, we can find only agonists, all the definition, and only one antagonist. Then we'll see. More recently, after the observation of the active site of these compounds, they were defined as allosteric modulators. No more agonists or antagonists or inverse agonists. They can be considered allosteric modulators, in particular positive allosteric modulators, old agonists, neutralizing allosteric modulators, old antagonists, negative allosteric modulators, old inverse agonists. This is the more modern definition and classification of these receptors. Allosteric modulators of GABA-A. Because they don't act on the active site of GABA. Here in the picture, you see the classification of psychoactive drugs. You see antipsychotic, anti-schizophrenia compounds, antidepressant, anti-anxiety, anti-maniac, and psychotomimetics. But we are not interested in hallucinogens, you see. We are now in this class, anti-anxiety, useful for anxiety and phobic states. And we'll see two other important classes, antipsychotic and antidepressant. So during the course, we'll see these three main classes of psychoactive drugs: antipsychotic, antidepressant, and anti-anxiety. And now we can see the chemical structure of benzodiazepines. We have already described their therapeutic use, their mechanisms of action, and now we can see the chemical structure of this compound. Here in the picture you see the general chemical structure. Two rings, A and B, fused together. Ring A is a normal aromatic ring. Ring B is quite different. Ring B is a 7-members ring with 2 nitrogen atoms and 1 carbonyl function. How we can define this type of ring? Following the nomenclature, we can define this ring as azepine. Azepine when you have only 1 nitrogen. Diazepine when you have 2 nitrogen atoms on this type of ring. In particular, you can see the 2 nitrogen atoms are in position 1, N1, and N4. In 2 positions, we have a carbonylic function, carbonylic group. And in position 5, there is another aromatic ring bound to the carbon in 5. So this general structure is called 5-phenyl because in 5 we have an aromatic ring. 1,4 diazepine. You see this 7-member ring. 2, 1, and because there is a carbonate in position 2. This is the general name. If you want, we can use also, just a moment, okay. We can open the Chem Office, so you can start to use this software. Okay. I have to share the screen, just a moment. Here. So we can take this one, and then you see there is a 7 ring here, and then we can put here the other aromatic ring, okay, and then we put the first nitrogen atom here, double bond, second nitrogen atom. Here you can see, put the oxygen, and then you can see the chemical name of this compound. You see the name 1,3-dihydro, okay, 5-phenyl, you have because in position 5 you have phenyl ring, 1,3-dihydro because there is only one double bond here. Benzo, benzo is referred to the A ring. 1,4-diazepine, the two nitrogen atoms. 2,1 because you have the carbonyl function. This is the general structure of benzodiazepines. The benzodiazepines present different substituents on ring A and on ring C. And now we'll see the structure-activity relationships of this important class of drugs. So, once again, I show you the slides, just a moment. Here, okay. Okay. Two important features are the ring A and the carbonyl function. These two chemical features are necessary to have the interaction with the active site of benzodiazepines. On the chemical structure of the benzodiazepine, we have already described the presence of two nitrogen atoms, and the first nitrogen atom on position 1 is close to a carbonyl function. This means that we have an amide group on the 7-member ring, the diazepine ring. If you remember, the lone pair in the amide, the lone pair of the nitrogen atom can be delocalized on the oxygen atom. So we can have a resonance form where the oxygen atom has a negative charge and the nitrogen atom has a positive charge. And there is a double bond between the nitrogen and the carbon of the carbonyl group. The negative charge located on oxygen atom, it is important because it forms a hydrogen bond with a residue of histidine present in the active site of the benzodiazepine. And it is important that this oxygen atom the location, it is important how the location of this oxygen atom, because this atom should be on the same plane of the nitrogen in 1. And this is due by the presence of the partial double bond between the nitrogen in 1 and carbon in 2. If we replace the oxygen with a sulfur, I remember you that sulfur atom has a lot of electrons, more than oxygen, and the hydrogen bond given by sulfur is less potent than that with the oxygen. In this case, if we replace the oxygen with a sulfur, we have a decrease in affinity. There is another double bond on the 7-member ring. You see this imino group is like a Schiff base. So we can see that this molecule, benzodiazepine, can stay on the plane of the breakboard, you see, because we have an aromatic ring, A, we have 2 double bonds, planar, and only the carbon in 3 position can flip downwards or upwards on the plane. So you can imagine this molecule when it interacts with the active site, you see a planar molecule except the carbon in 3 position. In this interaction, it is important the presence of ring A. Ring A is an aromatic ring, and we'll have a pi-pi interactions between the electrons present on the ring A with an electron cloud present on the receptor. It is important to have strong electronegative substituents in 7 position on the ring A in order to have a decrease of the electron cloud of aromatic ring A, and in this way this ring can receive part of the electron cloud from the receptor, from the active site. So we have the movement of an electronic cloud from the receptor, from the active site towards the ring A, which is poor of electron due to the presence of these electronegative substituents in position 7. It is important the absence of substituent of the imino nitrogen atom or on carbon 3. On your left, you can see the first benzodiazepines introduced on the market in 1975. Its it is called chlordiazepoxide. You can see that there is not a carbonyl group in position 2. There is a methylamino group, but after metabolization, the carbonyl 2 is oxidized to a carbonyl. We'll see the next during the lesson the metabolization, the change of chemical structure by our metabolism. Chlordiazepoxide is a very potent benzodiazepine, but it has a problem. Its activity is too long. This means that if you take a pill of chlordiazepoxide, the day after you have a problem such as hangover. If it is like if you are drunk, because it has a very long activity, the time. This was the first problem with the first benzodiazepines. They are too long time of action. So the first question for the scientists in that time was how we can control the time activity of this class, of this interesting class of compound. The answer was found in the urines of the patients. Why the urines? We can see together the last slide, just a moment, of this chapter. You see chlordiazepoxide here. This is the main pathway of metabolization of this compound. All compounds in red remain active. So, although some chemical change in its structure, there are a lot of metabolites still active. This is responsible of the long activity of this compound. So the scientists in that time had a smart idea to use the last active metabolite as drug to have a shorter time activity. They thought if we assume the last metabolite, it is sufficient a small modification of the last metabolite in order to block the pharmacological activity. This was the idea, a very smart idea, of the scientists in that time. So they investigated very carefully all the metabolites derived from chlordiaz epoxide, and they found that the last metabolite was oxazepam. You see here in red. Oxazepam is characterized by an OH group on carbon 3. Hydroxylation of carbon 3 by our metabolism. This means that this compound, oxazepam, is more hydrophilic than chlordiaz epoxide, can be eliminated very quickly, and this OH group, this alcoholic group on carbon 3, can represent a site of glucuronization. Glucuronic acid can react, can form an ester group with these alcoholic functions in order to have glucuronides which can be eliminated very quickly. This strategy to use the last metabolite as drug was victorious, was important, because in that time, after few years of the introduction of chlordiaz epoxide in therapy, the doctor used oxazepam. The commercial name in Italy is Tavor. And Tavor is very famous because slow time of activity, only one night, and no it represents the last metabolite, so it is necessary only small modification by our liver to modify this compound. So also for old people which use a lot of drugs, the association of the introduction of oxazepam in therapy does not represent a problem with their liver. And so really, oxazepam now is the most sold drug of this class in this time. So, have you any questions? Is it clear for you, this strategy? Very, very interesting. They isolated the last metabolite and they used this last metabolite as drug. Very, very nice.
Prof?
Yes?
I have written a question for you in the chat.
Okay, just a moment. I don't see the chat. Yes, let's see. I have a question. We all know the GABA relaxes in higher dose, but why in moderate doses induce anxiety? Janet, are you sure? in a moderate dose it induces anxiety? Yes?
I don't know because lo spiego in italiano, lo faccio prima. Praticamente avevo letto un articolo riguardo i neurotrasmettitori e a un certo punto c'era scritto per quanto riguarda i neurotrasmettitori GABA che un tipo delle dosi moderate induce ansietà, ma mi sembra assurdo perché comunque i recettori GABA normalmente rilassano e a livelli molto alti addirittura dicono uno stato quasi
di coma.
Quasi comatoso, ecco.
Sì,
Per
sì.
cui ero un attimino confusa sul fatto che dosi moderate possono addirittura indurre ansietà, cioè o è un errore di stampa oppure non lo so. Per quello che io chiedevo, perché sembrava strano.
Shanetta, I have never seen this type of effect. I don't know, because you're right, at low doses, I don't know. Perhaps you have no activity, or at low doses, perhaps the glutamic acid is more potent, you know, so you have a more potent effect of the glutamic acid in comparison of the activity of GABA. This is perhaps my opinion, but really, I don't understand this type of activity at low doses. Perhaps glutamic acid is more potent, and so you have the activity of the glutamic acid. Yes.
Okay, okay, thank you.
Okay. Other question? No. Okay. So, just a moment. Go back to this part. Okay. So, we have seen that it's possible to introduce a substituent on carbon 3. Just a moment. Yes. You see here the two important hydroxylated compounds present at the moment on the market. The first one is oxazepam. The second one is lorazepam. Lorazepam as an additional substituent on a ring C, but you see the general structure is the same of oxazepam with an OH group in 3 positions. So, we can introduce an alkyl substituent on the nitrogen. In this way, we can increase the lipophilicity of the molecule, and so we can increase the ability to cross the brain-blood barrier. But not bulky substituents, because they can prevent the interaction with the active site. Double bond, imino double bond is important. There are also different electronegative substituents on the C ring, especially in position 2. Here you can see we can introduce halogen atoms, which are very high electronegativity, and we can increase the activity of the compound. Here, at the end of the slide, you can see 2 very recent benzodiazepines. Instead of the amide group, they have a heterocycle system. This means that the receptor, the active site, can accept another planar region you see represented by this heterocycle, this triazolo ring. And this type of compounds have a better therapeutic profile than the old benzodiazepine. At the end, you see the chemical structure of an antagonist, of a negative, not negative, of a neutralizing ligand. Flumazenil interacts with the active site of benzodiazepines, but it is not able to modify allosterically the conformation of the receptor, but it still blocks the active site, and so can be used in case of a strong dosage of benzodiazepine, although this type of compounds is not so toxic. Flumazenil is present in pharmacy. You have to take this type of drug because in case of high toxicity of administration of benzodiazepines. So we can stop here for the moment. Have you any questions in classroom? At home? Any questions?
It's clear.
Okay, okay. So we can start about 11:40, okay, with this other important point. Okay, thanks for your attention. And then we take a coffee. Okay. Ok. So, we start again, and as I told you before, the conformation of benzodiazepine are almost planar. The conformation is almost planar because we have a partial double bond in the amide group and a double bond of the amino group. But if you see, the carbon in 3 position can stay on, over, or under the plane. So we can have these two conformers, these two different conformations of the diazepine ring. One with the tip, with the carbon in 3 under the plane, and conformation B with the tip of carbon 3 over the plane. And the scientists want to know the active conformation. But it was not possible to isolate these two different forms because at the room temperature we have the interconversion of the two conformations, so it is not possible to isolate the conformer B and the conformer A. In addition, these two conformations are two enantiomers. If you see, they are one the image of the other one. How we can stabilize, how we can isolate these two different conformations? It was possible by introducing a substituents on carbon 3. If you see, the scientists introduced a methyl group on carbon 3. In this way, you have two enantiomers, you see, because the methyl group can have can be an S enantiomer or R enantiomer, because we have a carbon 3 with 3 different substituents. If you remember, on the cyclohexane, when we introduce a bulky substituent on a carbon atom, normally the cyclohexane tries to arrange, to locate these substituents in equatorial position and not in axial position, because in axial position we have interaction with the other electronic clouds of the other atoms. In equatorial, the conformation is more stable. So if we introduce a methyl group on carbon 3, we can have the two enantiomers where the methyl group is in equatorial, and so we can stabilize the enantiomer S with the tip over the carbon 3 tip over the plane, or we can stabilize the conform R, the enantiomer R, where the tip is under the plane, you see. In this way, it's possible to separate these two enantiomers, and the scientists found that the most the more active was the S enantiomer with the tip over the plane instead of the other enantiomer with the tip under the plane. So we can say that the active conformation of the benzodiazepine is represented by this form where the carbon tree is over the plane. This is an additional information that can be useful if we want to design new benzodiazepine. And so we know the active conformation on the active side of this type of molecule. So now we can say that if we introduce a substituent on carbon 3, the more active the enantiomer is enantiomer S. What happens when we introduce an OH group on carbon 3, like in oxazepam? Also, in this case, the S enantiomer should be the most active of the two enantiomers. But, and in this case, it is necessary to isolate the two enantiomers and to use only the most active enantiomers as a drug and not the other one. If you see the composition of oxazepam, you can see that oxazepam is present in racemic form. And so it is not necessary the separation of the two enantiomers, although there is a substituent on carbon 3, and so we have a symmetric carbon atom. But why in this case is not necessary the isolation of the two enantiomers? If you see in this picture, you can see that it is possible to have the opening of the ring and then the closure again, and so we can have a change of the chirality of carbon 3. This means that we have an in vivo racemization. This means that it is not necessary to administrate a pure enantiomer because we have a racemization due by our metabolism. And so we can have again the two enantiomers starting from a pure enantiomer. This justifies the fact that oxazepam is sold in racemic form. We have seen the main components of this class of sedative compounds, but there are also other chemical structure able to give the same effect of benzodiazepine. In particular, you can see these natural compounds called beta-carboline. These compounds, once again, are planar compounds. You see two aromatic rings with another rings in the middle, but the their structure is planar, and on the second ring there is a carboxylic function, carboxylic group. Also, these compounds are known to have the same effect of benzodiazepines. But on the market, you can see these compounds called Z drugs. Why Z? Because all compounds present on the market start with the letter Z. So we have these imidazopyridines, imidazole, you see here the imidazole ring, and this is the pyridine ring fused together. This compound is called the zolpidem. Another compound is called zopiclone, pyrrolopyridazine. Pyrrolo, you see this ring with one nitrogen, is a pyrrole. Pyridazine is this ring with the two nitrogen aromatic with two nitrogen atoms. Pyrrolopyridazine, you see. And the zaleplone is another one. Pyrazolopyrimidines. Pyrazolo is this ring with the two nitrogen atoms. And pyridazole, pyrimidine is these other 6-member rings with two nitrogen atoms. All these compounds start with the letter Z, and so they are defined as Z drugs. Also, these drugs have the same activity of benzodiazepines. They exhibit a planar cycle, you see a planar backbone, but probably their site is different from that of benzodiazepine. These are the most recent compound used as a sedative and present in therapy. Z compound. So now we have a part of the synthesis of chlordiazepoxide. This synthesis is not requested. It's a very difficult to understand that it's not requested for the exam. But also, I want to show you what happens in 1975 when the scientists discovered the activity of this class. In particular, in that time, the scientists wanted to synthesize not the benzodiazepines, but they want to synthesize this different structure. If you see ring A, the same, another 7-member ring, but, okay, with two nitrogen atoms, but with an oxygen. Oxadiazepine. In that time, the scientists wanted to synthesize this structure and not the structure of benzodiazepines. And in that time, the scientists were convinced to have this structure with oxygen. In reality, in that time, they had the chemical structure of chlordiazepoxide. So, it's just to say that the discovery of benzodiazepines is related to a mistake in the recognition, in the identification of the final compounds of the synthesis. you can understand in that time the NMR equipment did not exist in that time, and they used also only infrared spectra and the UV spectra. Perhaps, sorry. And in that time, they couldn't have other equipments to investigate the chemical structure of the final compounds. But how the scientists tried to synthesize these benzodiazepines? Here you can see the chemical synthesis. The most important compound, the starting compound of the whole synthesis, is represented by this ketone. You can see the chemical structure of this important ketone. An aromatic ring, and the other substituents is another aromatic ring with different substituents on the aromatic part. So we have an asymmetric ketone with the two aromatic rings, but two different aromatic rings. If you remember, when you want to synthesize an aromatic ketone, we can use the well-known chemical reaction called Friedel-Crafts acylation. We need an activated benzoic acid. You see, we have the chloride of the acid, of the benzoic acid. We have an aromatic ring activated by the presence of this amino group. And we have the acylation. Normally, this compound is able to attack the position 2 of this aniline derivative, because the position 2 is activated by the presence of the amino group. But in that time, the problem was that this reaction can give different compounds. So these are the intermediates. This is the first one. You have the acylation in the right position, if you see, but also the activated acid is able to attack the amino group. So we have a double insertion of the activated benzoic acid. And then in addition, once again, the amino group of the anilino derivative is able to give an additional attack on this carbonyl. You see the formation of this OH. A rearrangement of these three substituted compounds is the attack of this nitrogen to this carbonyl compound, the elimination of a water molecule to have the ring closure and to have this pyrimidinic intermediate. Fortunately, in acidic condition, we have the hydrolysis of the pyrimidinic ring to give the asymmetric ketone. And this is the first step. But we have now our starting point. From this compound, the scientists tried to synthesize the 3-oxabenzodiazepine. How they tried to synthesize this compound? starting point, our ketone, treatment with hydroxylamine, the lone pair of the nitrogen atom is able to attack the carbonyl compound, elimination of a water molecule, and we have the Schiff base called oxime. And this is the first step. The second step is to have the other part of the 7-member ring, and so they used this activated acetic acid. You see ClCO is the activated acetic acid with the other methyl atom with a chlorine here. In this way, once again, the double, the lone pair, the anilino group is able to attack the activated carbonyl compound, and we have the amide function here. And now the scientists tried to close the 7-member ring in order to have the 3-oxadiazepine ring. They wanted to close the ring with the attack of the oxygen. In particular, they believed that this oxygen was able to attack the carbonyl of the amide. This is the mistake, because the oxygen is not able to attack the carbonyl, but the nitrogen atom of the oxime is able to attack the carbonyl of the amide group. So in that time, they get the ring closure with a pyrimidinic ring, you see here. They obtain this quinazoline N oxide. Quinazoline is the whole system, N oxide. And then if you see, or perhaps it's just here, just a moment, we can change. So, okay. And then you see there is this activated carbon atom. They wanted to replace the chlorine with an amino group because they want to increase the hydrophilicity of this molecule. They use the reaction with this methyl amine with the quinazoline oxide is responsible of the ring expansion in order to have a 7-member ring. In that time, the scientists believed to have an oxygen atom in 3 positions. And they investigated the activity of this compound, and they found that the activity was very interesting on the rats because this compound showed a very potent sedative activity on rats. But some years later, other scientists carefully investigated the chemical structure of the compounds, and they found that the chemical structure of the active compounds did not contain any oxygen atom on the 7-ring part of the molecule. So all this synthesis just to explain you how sometimes it is possible to have false information from equipment, from data, and so on. It is necessary a right interpretation of the different data. Another important point is represented by the chemical structure of this ketone. This ketone is used now as a starting point for the synthesis of benzodiazepines, but following a very easy synthesis. This is the synthesis of oxazepam. This is requested for the course, but fortunately it starts from this ketone. So I do not ask you how to synthesize this ketone, but this is the starting point because it is commercially available. And so the starting point is represented by this ketone, and a simple reaction with a protected amino acid called glycine. Glycine, if you remember, is the most simple amino acid of the whole series, of the whole 20 natural amino acids. And in this case, we have an esterified form of the carboxylic acid. Ester can be considered an activated form of an acidic group. And you have also the amino group of the glycine. So the reaction is very simple. If you want, we can describe this synthesis on the ChemDraw. So just a moment. I open again ChemDraw. I share my screen. Just a moment. Okay. So we can. Okay. You can see the two different parts here. You have the ester here, ethyl ester, and then here you have the ketone. So what happens in this synthesis? You have an attack. Oops, no, it doesn't. Just a moment. I use another one. This one. Okay. You have an attack of the anilino group on the carbonyl of the ester function. And also you have another attack of the amino group of glycine on the carbonyl compound, on the carbonyl group of the ketone. We have an elimination of a water molecule. So, and then we can have the formation, the 7-member ring here, here. Oops, sorry. Oh, there is a water molecule. No. Okay. Once again. Okay. And then the formation of the other bond here. Then, oops. Oh, not so nice, but you see. We have the formation of the 7-member ring by a reaction starting from this ketone. If you remember, there is also chlorine here. And so we have the Cl also in this compound. We have the ring closure and the formation of the 7-member ring, the diazepine ring, by a simple reaction of the ethyl ester of the glycine with this asymmetric ketone. It is a very simple reaction, only one step. And now the problem is how we can insert the OH group in 3 positions. It's not easy because we have to make a selective oxidation of the carbon in 3, but it's not easy. There is another pathway. There is another way to introduce the OH on carbon 3. We can oxidize with the hydrogen peroxide the nitrogen in 4. So hydrogen peroxide, then we have the oxidation and oxide of this nitrogen. Okay, and then we have also a negative charge on the oxygen and a positive charge on the nitrogen. After oxidation, we can esterify this oxygen with acetic anhydride. Acetic anhydride, just a moment. Acetic. Remember, acetic anhydride is an activated form of acetic acid. What happens in this case? The oxygen with its negative charge is able to attack the carbonyl of the activated of the anhydride, and then we have the formation of the ester. Just a moment. Okay. And then press. And then than this one. You see, we have esterified the oxygen atom of the N oxide by reaction with the acetic anhydride. This compound is unstable, and so after heating warm high temperature, I have a migration of the acetic group on the carbon tree. You see this we have the formation of an oxygen bond with a carbon tree. So we have the migration of the acetic group from the position 4 to position 3. This migration is called Polonovsky transposition. The mechanism is unknown. Perhaps the scientists were very lucky because they observed this migration of this group on the carbon tree. The result is that they obtained this compound you see, the ester group is migrated on carbon 3. And now the last step is only an hydrolysis of the ester to release the OH, the alcoholic function. Very simple step. In basic condition, you know, it's possible to have the hydrolysis of an ester to release the OH group on carbon 3. So we can see now this synthesis on slide. And so if you have any question, I can explain you the different steps of the reaction. Just a moment. Okay. So once again, you see the starting ketone, the asymmetric ketone. The reaction with the glycine, the activated ester of glycine, ethyl ester of glycine. In basic condition, you have the ring closure. Just a moment. Oh. Okay, don't know. It's not possible. Okay. Oh. Oh. And so the anilino group is able to attack the activated carbonyl to give the amide. The second, the amino group of the glycine is able to attack the carbonyl compound. Water loss of one molecule of water is lost. And then we have the formation of double bond, shift base. Oxidation with the water peroxide to give the N-oxide. Reaction with the acetic aldehyde to esterify this oxygen of the N-oxide group. You see, this intermediate with the ester on the oxygen of nitrogen in 4. And then Polonowski transposition. You see, we have the formation of an oxygen bond with the carbon 3. And then basic hydrolysis to release the OH in 4 position on carbon 4. Have you any questions? At home, have you any questions? Okay.
No, so far.
Okay, grazie, Jeanette. So you see, the synthesis of this molecule is not so difficult, only 2 steps. One, condensation of the ethyl glycine, and the second is esterification, with a transposition and hydrolysis. As I told you before, this compound, oxazepam, is a bestseller in pharmacy. More than 30 years ago, I worked in pharmacy for a lot of time, for 3 years. And in that time, during the day, perhaps we sold about 100 boxes of oxazepam every day. And so you can imagine the general use of this compound.
It can be taken without prescription?
No, it is necessary, the prescription of the medical doctor. But nevertheless,
The doctors seem to prescribe that as standard.
yes, because these compounds are not so toxic. And the patient, okay, you know, especially the elderly, wants to have a pill to take, sleep. And so it's these compounds are very common, really.
Yeah, but nowadays anxiety is a problem of teenagers also.
Oh, yeah. They can be used also in children, because sometimes when you have children not able to sleep, but I was a parent and really I prefer to stay with my children because the use of drugs in the small children, I think it's not the right solution. Yes, but sometimes the parents prefer to give a pill. Yes. Yes. Another very simple synthesis, if you want, is reported in this picture. You see only one step. Use this derivative of acetic acid, activated acetic acid. Once again, the anilino group is able to attack the activated carbonyl. And in presence of ammonia, it is possible to form the ammonia, the beginning attack, nucleophilic substitution on this carbon, with the bromine, and then the attack to the carbonyl to give the Schiff base. It's a very, very simple synthesis. And what else about this type of compounds? Just a moment. Okay, we can close. Okay. So we have already seen the metabolites of chlordiaz epoxide. The last metabolite is represented by oxazepam, you know. And this compound can have problem of abuse because their action is pleasant. And this is perceived by healthy subjects. Mental addiction, this is the problem, mental addiction. Psychological addiction. If I don't have my pill, I am not able to sleep. Here it is in Italian, but you can see how many benzodiazepines are sold in our country. You see about, the average is about 53 doses for 1,000 inhabitants. You see the region with the highest prescription of benzodiazepines. And during the pandemic, COVID-19, it was observed an increased use of these compounds. And also increased, you see the addiction, dipendenza. In Italian we say dipendenza. The addiction, people with these drugs. Okay. Have you any questions about this chapter? Okay. At home? No?
It's everything clear.
Okay.
Thank you.
So, if you don't have any question, we have finished